Okay, what follows are some practice problems with the concept of acceleration, but no new material will be covered. Acceleration is the first physics concept that proves squirrely for people, that's a little slippery and they have to work on. So I thought we would just have some extra things up. If you're feeling comfortable, you don't have to do them, or if you want to fast forward through a lot of this, that's perfectly fine too. Alright, if an object is speeding up, is it true that A, its acceleration is negative, or B, its acceleration is positive? Sorry, A, its acceleration is positive, or B, its acceleration is negative, or C, its acceleration could be positive or negative depending on the direction of its motion. So pause the video, come up with your own thought, and then play to find out what it should be. Remember, if I'm just getting faster, it could be something which is moving to the right, but getting faster, in which case the acceleration aligns with it, and so we would end up with something like that, and that would be the acceleration greater than 0. But instead we could also have a thing which is moving to the left, but getting faster, in which case the acceleration would be aligned with it, and it would seem to be negative. This is of course assuming that we take our standard axes, that plus x points to the right. So we see that it ends up depending on whether the object itself is moving left or right, so it could be either based on that. Alright, Carmela and Desi leave their physics classroom separately and travel west. They are both starting from rest. Desi left first, traveling with an acceleration of 4 meters per second squared for the first 6 seconds, but then he traveled at constant velocity. 2 seconds after Desi started, Carmela began with an acceleration of 3 meters per second squared for 10 seconds, and after that she traveled at constant velocity. And we want to graph the velocity of both travels as a function of time up to 16 seconds, using t equals 0 when Desi leaves the classroom, making his line blue and her line red. So take a moment, maybe sketch it on the side, or at least in your mind's eye, figure out what do you think it would look like, and then we'll see. Alright, we'll start with Desi in blue. And we're told that he starts at rest, so his velocity should be 0 here. And then has an acceleration of 4 meters per second squared, which is the slope on a velocity graph. So for the first 6 seconds, he gains 4 meters per second every second, so he ends up at 24 meters per second, which would be here, and it would be uniform, so something like this. And then he travels at constant velocity, which means that his line is horizontal. So that's not so bad. Let's talk about Carmela. Carmela waits 2 seconds and then has an acceleration of 3 for 10 more seconds. So her first 2 seconds, she has 0 velocity. She's still at rest. And then she gains 3 meters per second for each of 10 seconds. So after 10 more seconds, which is 12 seconds on the clock, she's at 30. So she should do something like this. And then she travels at constant velocity. So we get this. This is Carmela. This is Desi. And they end up something like that. A particle has a velocity v1 as it moves from point 1 to point 2. The acceleration is shown. What is its velocity vector v2 as it moves further away from point 2? So we look over here and we say, well, take a second to consider it. Alright, we have that the velocity, the acceleration is pointing opposite to the velocity, so it should reduce the velocity. It should be smaller, but it's a small change. So most likely, it's not enough to undo the velocity, and so we end up with this, a smaller downward velocity. To be fair, they didn't give us, we're missing delta t. And the larger delta t is, the more the change will be. And so conceivably, you could actually argue on C or D or E if delta t had been large enough and the acceleration were constant. But the way they set it up, it looks like I'm pretty sure that the idea was to be B. Alright, a ball is moving to the right and traverses the ramp shown below. On the next screen, we'll sketch a graph of the velocity versus time, and directly below it, using the same scale for the t-axis, the acceleration versus time. And then, so we'll see. We want the velocity versus time, and then the acceleration with the same t. Okay, so at first the ball rolls. So we'll just have the ball roll like this. I'll pick an arbitrary time, I don't know. Then it goes on the ramp, and we know at the bottom of the ramp, it's going to be going faster. I don't know how much faster, but something like this. And so between those times, this. Now, the assumption here is that it accelerates constantly, which, to be honest, was not justified in the problem, but turns out to be true, that the acceleration down the ramp will be constant. And so now we want to say here, and if we take, as we are, sort of, and we're being careful here, I guess we're being a little careless, what are the positive directions? Well, it's pretty easy to call that plus x. And then we're going to say along the ramp is plus x. So we've done a weird thing where we're letting our axes sort of be 3 different directions, but that's fine. And we say, well, during the first 2 seconds, there's no acceleration, or first whatever number of seconds. When the velocity is constant, there's no acceleration, which means also when the velocity is constant at the end, there's no, right, the acceleration is 0. But in between, the acceleration has some value. I don't know the scale, so I'm just going to pop it up to some number. We have the disturbingly aphysical vertical motions here because we act like the velocity instantly starts changing. In a real, if you could really zoom in with a high-speed camera or whatever, you'd see that there'd be an acceleration that starts from 0 and goes up to that value. So the velocity is not really linear, but has some little curve. But we'll assume that happens so quickly that it doesn't show up on our graph, and we get something like this. Mike jumps out of a tree and lands on a trampoline. Brave Mike. The trampoline sags 2 feet before launching Mike back into the air. At the very bottom, where the sag is the greatest, Mike's acceleration is A, upward, B, downward, or C, 0. So take a second, think about what you want to say, and then we'll continue the video to say what actually happens. Here we want to say that Mike's velocity is 0, and then a little bit later he's moving up as the thing pushes him up. So he had to accelerate in that direction. Right? It's a little counterintuitive, but he's come to rest and he's about to move upward. His velocity is about to be moving upward, so he has to accelerate in the upward direction. So it is A that comes out. All right, a cart slows down while moving away from the origin. What do the position and velocity graphs look like? Take a second to form your answer. All right, keep in mind there's sort of this weird, let's do it here. The division is like this. Those are your 4 answers. And we want to say, well, looking here, its position starts at the origin. Well, we actually don't know if it starts at the origin, do we? So we shouldn't use that one. But it is slowing down. So its velocity should be, it was moving away but getting slower. So it should have a positive velocity, but a negative acceleration, which is, remember, the slope on VT graph. So I look through all these, and let's say the VT graph, it was moving, and then it's getting slower. So here, no good, because the velocity was at 0 and it's getting faster. And this one is no good, because the velocity starts at 0 and gets faster, just in the negative direction. And that's not what's happening. Then we want to say it should be moving away from the origin, so it should have an initial positive velocity, so that kills this one. So it must be case D, which we then confirm also has the slope has to be negative, and it is. You'll note here that I did not actually in any way consider the motion of the position plot, the evolution of the position plot, in considering the motion of the cart. I didn't need it to eliminate the choices, so I didn't even look at it. If we look at the part, we see, okay, it's moving away from the origin. That doesn't make clear that it was at the origin at the start, but apparently it was, and then it's moving up, but getting closer and closer to horizontal because its speed is becoming closer and closer to 0, and on this kind of graph, the speed is the tangent. Same kind of set. A cart speeds up while moving away from the origin. What do the velocity and acceleration graphs look like? And then they give us this picture which says that's already in the positive side. So if it's on the positive side but moving away from the origin, its velocity must be positive. So we'll start with this. And if it's getting faster, then the acceleration must also be positive, but may be constant. They didn't actually tell us. So if we look at our, let's make clear again that we have this weird quadrant thing. So the velocity is positive and the acceleration is positive, so A would work. But then, sorry, A doesn't work because the velocity is positive, but then constant. And I need the velocity to be positive and increasing. So A does not work. All right, for B, we have a velocity which starts at 0, where it's not very clear, but it is definitely getting faster as it moves away and has constant acceleration, so B is possible. C is out because while the velocity is doing the right thing, A is not constant, and A needs to be the slope, so these don't work. And then for D, the velocity has the correct kind of behavior, but the acceleration is not the slope again, so it's out. So we're left with that it must be B, the only one that has the correct slope and matches the acceleration to the velocity. Here is a motion diagram of a car which is speeding up on a straight road. Remember, we can see from the way the arrows go, the car starts here and then goes like that. And we want the sign of the acceleration a sub x, and we want to know if it's positive or negative or 0. Take a moment to consider and then resume the video when you have an answer. So here we have a velocity which is 0 and getting faster, which means at the acceleration is same sign. So since the velocity is negative and the acceleration is the same side, the acceleration must also be negative. A cart speeds up while moving towards the origin. What do the velocity and acceleration graphs look like? Moving towards the origin, but as we can see here already on the positive side, means the velocity must be pointing leftward, so the velocity must be negative. And it's getting faster, so it should be getting more negative. So before we look too far at the acceleration curves, let's see if we eliminate anybody by using just the fact that the velocity must be negative getting more negative. Not good. This is not good. Even though it's getting has the right slope, it's getting more negative, getting less positive, but it's on the wrong side. So we're down to either C or D. And then we want to say, well, which of these things are consistent? And we can see that the slope is negative in both cases. So the acceleration should be negative. But in case D, the acceleration is positive. So we're left with, it must be C. That is the correct behavior. Which velocity versus time graph would go with the given acceleration graph? So we see that the acceleration is a constant but negative thing. So we need the slope of the velocity curve to be, the velocity curve needs to be a line which is sloping downward, and then suddenly a line, a line which is sloping upward. So if we look over here and we say, which of these work? That's not a line sloping downward and then upward. This is a line sloping downward, but then sloping downward some more. This is a line sloping upward and then sloping downward, so that's no good. This is a line sloping upward and then downward, so it must be this one.